gotta admit, this afternoon session is kind of a grab bag of topics, but I think they're all pretty interesting topics. So maybe that'll be good, right? You don't have to sit down and plow through an hour and a half of anything. If you get a little restless, then we'll go to the next topic. Yeah, I'm going to start on this tool called dharshan and how we're using it to help us understand how these applications behave I/O-wise at large scale. Again, to be clear, Phil Carnes did the lion's share of the work on the project, and Kevin Harms helped us understand what's going on at ALCF. Katie Antipis and Yushu Yao did a lot of work at NERSC to help us understand what's going on over there and help us with integration problems with their systems. And so this is, again, one of those group efforts that has really paid off. I think we started working on this back in 2008 or 9. When we got our Intrepid machine, the idea being, there had been a study of workstation I/O activity called Charisma, and it was heavily cited, but the data was early 90s, so it's been time for an update of this information, and we have access to a leadership class machine in our, well, not our basement, but around the corner from us, so we should be able to get in early and then instrument these applications. But no one would put up with that if it got in the way, right? The nice thing about the dharshan approach is that its design and its implementation is all meant to be virtually transparent. I think the worst case overhead at a significant fraction of Mira is something like 25 seconds at shutdown, and when these jobs run for multiple hours, I don't think anybody's going to make a fit about an extra 25 seconds of shutdown time. So, let's see. Right, so lightweight, unobtrusive, but yet collecting enough information to still be useful. So what does it collect? Well, it collects information about how many operations are happening, right? Counters are lightweight because they're just a number you increment, not a trace of what happened when. And we can do that for POSIX, MPI-IO, ParallelNet CDF, HDF5. We can take a look at how much I/O, what kind of I/O is happening that's aligned and unaligned. As we remember from earlier, our locking file system discussion, aligned I/O can make a big difference in writes. We can keep track of timings because, again, first the time from the first and the last is one value. That's a timestamp, and these are the kind of things we can collect and not grow our log data very much. And then histograms make a pretty nice data structure in that you're just updating counters and bins, and that can, again, that's bounded overhead for a file. We look at the different kind of I/O patterns. Sequential, I/O is happening, increasing offsets through the file versus running backwards through the file, which could happen. Maybe it's consecutive, one I/O is happening right after the other, or stride would be if there's a even gap between the files, and then that would suggest that there's a little more structure to the file than originally may have been expected. So, so we call this tool dharshan. Dharshan's a Sanskrit word for sight, giving us insight into the internals of these applications, and we use it as sort of a first step on triaging how these applications are doing, how they're doing I/O and why they might be having problems. Right? We trick the applications into using us by they call MPI-CC or they call the linkers to link their applications. Well, we kind of sneak dharshan into those wrappers, and so now with various MPI profiling tricks, I'm going to show that jump shot graph, which comes from the profiling interface, and then that captures the MPI calls. And then we use some LD wrapper tricks to capture the POSIX calls. We do have to relink the files, relink the applications, but once you've done that, instantly, from that point on, logs just show up in the file system, ready to be captured and studied later. We have quite a large collection of logs on Intrepid, and we've already started collecting data on Mira. How do we keep it lightweight? Well, again, we talked about statistics that are bounded in overhead, and then where we insert ourselves into the I/O code path also helps. We can keep data updated in memory during execution time, and then at MPI finalize, we then gather all the data and then write out the file. So we do miss a couple classes of applications then. Applications that are never using MPI, which on Intrepid is somewhat small, but on a machine like NERSC is not necessarily zero. Then projects that blow up, either because there's an error or sometimes projects have the model of I will run until the wall clock time expires, at which point I'll restart from a checkpoint and continue to run. So that ends up actually being a non-trivial portion of jobs at NERSC at least. I think that's a little less true. That's less the case at on Intrepid and Mira. But again, that's an aspect of the design that we have to kind of rethink maybe as we want to cover. We've already gotten pretty good coverage on applications, but there's another class of applications we can expand to if we think a little bit more about how to do this. Right, so we ported on Blue Gene and Cray, and so now on all the leadership class machines, on Intrepid, Mira, and Hopper, you can get these logs. We've also used it on some Linux clusters, and you can put on your laptop too, which I've done it for some workloads. Once you've run your program and you've dumped all the data out to a file, then you have sort of what do you do with this? It's 158 counters per file, and sometimes you just look at the plain list of counters, but that can be a little overwhelming. Instead, we've got a script that will process the file and give you a 3-page PDF report. And I've got on this slide, we've got sort of a discussion, and over here we zoomed in on some of the more interesting graphs that might be hard to see at this slide resolution. So we'll just walk through the four graphs and the 2 tables. This first bar graph is sort of describing, we know how long the jobs ran, we know how much time was spent in I/O and how much time was spent in MPIO and POSIX. So we can look at how important was I/O to this job. Turns out it was, some 40% of runtime. So that might be worth a little more attention. The rule of thumb is if you're less than 15-20% of runtime, then your I/O is not really a problem. But here's suggesting that that we can think a little bit more about I/O and try to make that a smaller portion of overall runtime. The blue bar is kind of hard to see it on this graph, but that's describing metadata. That's anything that isn't a read or a write. So opening files, closing files, seeking around and syncing data, which if you have, for some workloads can be non-negligible. Operation counts helps you kind of make sure everything's sane. If you saw a billion seeks or a lot of other strange calls, that might trigger a question to the application author, which is a nice change. Usually it's the other way around. The application person comes to us and says, I have a bad I/O problem, help me fix it, and they're asking us the questions. But we can look at this report and say, I see you doing a lot of seeks. Why are you doing that? Or what do you think's happening here? Or why is, you told me you were doing checkpoint I/O, but I see a lot more reads than I was expecting from you. So this is sort of a first pass, understanding what sort of workload. In this case, you see no reads, some independent MPIO operations, and no collective I/O optimization operations going on here. This histogram of I/O sizes is pretty helpful to me. I look at this and I say, okay, nothing in the tiny, small file regions. A lot of big I/O happening here, and some of these are, not huge, but we can still live with that. That should be fine. And then the I/O pattern. This is the sequential and consecutive distinction that I talked about a few slides back. Here we have a table of access sizes. So what's the interesting thing here is that even though there are 129 files, the number of headers that are being written is a lot more than we'd expect, about 4 times more than we'd expect. Right there, that's an interesting question. You must be something's going on that is a little bit wasteful here. So we can, there are a lot more examples of this sort of behavior that dharshan has flagged, but this is just a quick sort of. You can do a couple things once you've started collecting this data. Like I said, first it solves the several rounds of emails between a computational scientist and an I/O person about what's going on. Instead, the exchange is, in fact, sometimes the exchange is, I ran my application, I got strange I/O results, I made you a PDF, tell me about what this is telling me. And that's a pretty good way to start that conversation. It's not the end of the conversation, but it's a great way to start. That's good on an individual basis. Now you can also think a little bit bigger picture. We've got logs from 30 to 40% of all the jobs. Why don't we put a little data analysis, apply a little data analysis to the problem, and proactively detect applications that are doing I/O less than ideally, and then go out and talk to them before they waste any more of their time in I/O, and before they even notice they have an I/O problem. So you have been here in this class all day, and now you are I/O experts, and you will not make any of these sort of mistakes about what applications are doing. But people who haven't been in this class might make these mistakes. So don't laugh too loudly, but we think about some rules that might warrant further. So some rules that would raise some questions. If you see applications that are reading more data than the file is big, well, that suggests that there's a lot of redundant work going on there. If the file is a gigabyte and you're moving 6 gigabytes of data through the read calls, maybe there's some data you could skip reading, or you could cache better, or maybe you've got something going on that you weren't aware of. Because again, software stack has lots of layers. Maybe there's a page-based caching layer somewhere that's turning your small reads into big reads. Who knows? But it's again, the start of a conversation. We talked about how dharshan is capturing metadata times. So if open, close, stat, seek, if all that is more than 25% of your runtime, that suggests that you got a metadata problem. We talked about how directories are kind of like doing I/O to a file, but they don't get quite the same attention. So this might suggest that we need to talk to an application person about rethinking the way they do I/O to this file system. Maybe writing to one HDF5 file instead of creating a million. On the same flip side of that, if you see jobs writing a small amount of data, and we just pick 1 megabyte as being this threshold, but if they're all writing to a shared file and they're not using collectives, right? Think backwards. If you did big I/O to a shared file without using collectives, well, okay, no big deal. Maybe you could get a little more performance, but you already, you saw that block size, transfer size versus bandwidth graph. You're already up on the good regime of performance, so you have other things we can worry about first. But there are people writing small amounts of data to a shared file that would benefit from collective I/O, possibly, or some other approaches. So this is data we took from the Hopper machine. So the workload is going to be a little bit different than at Intrepid or Mira, but but we could still do the same sort of preemptive study once we've collected a large enough sample of logs. So redundant reads. We're great in shape. Okay, good shape. And again, talk about this. Really no reason to read the same data from lots of processes. There's plenty of layers in the software stack that can make that happen without moving data. There are, the transfer from storage into memory is going to be pretty expensive as it is. Don't do it more than once. So maybe some thresholds here. If we're moving more than a terabyte of data, and that's larger than the file, we'll go examine that. Oh, it turns out 671 jobs match that description. So all three of these examples always surprise me. I always think of this as, well, no one's going to be doing that, but then we always find hundreds of examples meeting these criteria. So here, of those 671, here's the worst offender. It's a 6,000 process job, which is pretty good size for Hopper. I forget how big Hopper actually is, but that's several thousands of processors. That's great. It's running for a long time, but half an hour of that time is spent in I/O. 457 times more data being moved than exists in the file. Not only that, it's 8 kilobyte read sizes. So, gosh, that's going to so this 27 minutes of time spent in I/O, yeah, okay, it's not a huge portion of their 6.5-hour runtime, but they could get that half hour back probably down to a few minutes, and then that's getting more time for science and less time waiting for their I/O to finish. All right, so again, metadata operations, it's not reads, not writes, but operating on files in a directory. Okay, so the threshold here. If you spend more than 30 seconds per process, and again, these are thousands of processes, so that adds up to be a lot of time globally. And if it's a small job doing metadata, well, we're not going to worry about that because there's not much we can do about that. But bigger jobs, and it adds up to be more than a quarter of the runtime. Now, gosh, that's a lot of conditions. 252 process threshold, 252 jobs match that condition. Okay, so who's the worst offender here? It's one that is, oh my goodness, 200,000 files, writing to each one about 3 times and statting each file 3 times. Okay, maybe I can understand writing 3 times to each file, but there's no reason to stat it every time you do that right. I mean, it's not changing that fast. The stat is, yeah, it's a file. Yeah, it's still a file. Yep, still has this permissions. I guess they're monitoring the file size or something. But what probably is happening is there's something going on in the library, right? So we can start talking to the application person about this again and figure out what's going on. So okay, why is this going on? Well, probably lots of files. So yeah, think about using a high-level I/O library. Think about maybe come up with some different way of structuring data where instead of 1 file per process, it's 1 file per group of processes. If you can't go full-on I/O library or some other solution there. As Quincy says, there's only one end of file, so yeah, you stat to see where you need to go. But yeah, all their I/O time, they're running for 200 some seconds. Half that time is I/O, and almost all that I/O time is metadata. So again, do little modifications here, and now they could be doing they could be running probably 50% faster. So we've talked about sometimes shared file I/O is a challenge. That's why PLFS exists, and that's why Adios exists. But if you're going to use a shared file and you're going to do small writes to it, well, that suggests that maybe there are some better approaches. Right? You as an application maybe only operate in terms of 8K chunks, but all these different I/O software stack layers exist to do those transformations into the file system friendly request sizes. So all right, if we have more than 100 million operations and no collectives. No collectives. I spend all my life telling people use collective I/O. Surely people are using collective I/O. Nope, 230 jobs. Okay. Well, okay. So we found a 128 process job that was spending half the time half its time in I/O. So what is this? 100 bytes, doing 5.7 billion writes of 100 bytes. Yeah. So no wonder they're getting a megabyte per second, right? I mean, if you've learned nothing else from today, don't do 100 byte write to your file, and you'll be ahead of the game apparently. Yeah, if you can't hear Rob in the corner, file systems are a globally shared resource, and this 128 process job was probably flattening the file system for anybody else running on this machine, and probably a denial of service attack, as Quincy mutters under his breath. And so then, yeah, people are like, hey, your I/O system's horrible. My performance, which is usually hundreds of gigabytes a second, now went down to 0. Yeah. We can now we have tools to tell us who broke the file system. What was I going to say? No matter. Denial of service. Quality of service, right? You could imagine that we solve this problem in networking with quality of service tools. The state of storage is not such that quality of service is widely deployed, if at all. So maybe that's one reason to think about doing that. Anybody can, again, shared resource, people abuse it. So you're right, fixing this problem would be good not just for this guy, but for everybody else running on Hopper and whatever machine he goes on to next. Right, so these were those three scenarios were done as part of a Cray users group paper, kind of describing what we've learned from our deployment at NERSC. We've got a couple other examples we've learned from. These are more, and those were done with automatic sort of. Here are the logs. We'll find interesting case studies out of this. The next couple of stories were done more manually, the old-fashioned kind of legwork way, where somebody came to us and talked to us about what's going on. So here's a combustion code called high-speed combustion dynamics, HSCD. Simulating the explosion of some confined gas. In this case, there's 8,000 processors, but they're working on 16,000 files. Yeah, that's going to be a problem, especially on GPFS. So look, here's your I/O use time. Okay, I don't see any green or red here because it's all spent in metadata. And on GPFS, there's a well-known problem of creating a lot of files in one directory, and maybe 16,000 isn't really a lot, but for GPFS it is. It'll spend all its time grabbing locks on the directory, and this is kind of the hallmark of GPFS. Yeah, you can make about 10 files in the directory and then you're in trouble. So no problem, we can fix this, and we did. So we talked with Alexei, what are you trying to do? Can we try these different approaches? And Alexei was game. He tried 3 or 4 different approaches, and each one got him some improvements. And I think I can talk to it better over here. So, like I said, creating directories in parallel on GPFS is going to be a big headache, but there's no reason why you can't create them ahead of time. And if you do that, rank 0, or maybe even a shell script before you submit the job, makes the 16,000 files, you'll get, what is this, how many zeros do I add to this? 100, 200 times better performance, 300 times better performance. Well, hey, pretty good, great, yay. We can do better. We understand his code, what he's trying to do. What he wants to do is sort of checkpoint what's going on. All right, well, this is a natural fit for collective I/O because everyone's got a work unit and they've finished their simulation. They want to do I/O. So why don't you write to a shared file? You have a small header. You do it. You could use parallel netcdf or HDF5. No, I don't want anything complicated. Okay, here you could use MPI/O. Fine, no problem. We almost doubled his performance just by using collective I/O to a shared file. So what's going on? Once we get down here, 8 files and an I/O time now. There's some communication going on in MPI/O as they coordinate with everybody about what data goes where. But when it actually comes time to send data out to the file system, it's almost no time at all. In fact, as we looked at this a little bit more, I think we can make it even better. Revisited this workload and the process found some other improvements. The story is pretty familiar by now. I don't know anything about combustion simulations or computational fluid dynamics, but we can look at these sort of API, the way these applications using these API and these software storage layers and these system storage software layers, and make suggestions that help them get more science done in less time. Good. It's been great. We have this guy, Turco, who you met yesterday. He works 2 doors, 3 doors down the hall from me, and I could always count on him to do 2 things. Follow our advice about using high-level I/O libraries, or at least MPI/O, and then bug me when it doesn't work the way he thinks it's supposed to work. And so another one of those cases, hey, Rob, I got this I/O scaling thing. Shouldn't should I/O increase linearly with the number of processors? No, Tom, it should not do that. I will work on that. Let's see what's going on. Tom tells me, hey, I've got this file format. It has a header here and some data, and because there's variable amounts of data on each processor, I'm going to have a little bit of this kind of like this append, header and analysis, header analysis. So let's have everybody write out the header and then write out the data, because that makes sense, right? Logically, you've got this information, then write that out. Okay, and all right, Tom, that sounds good. Are you doing any gaps in your I/O? Oh, no, there's no gaps here. It's contiguous. All this stuff's written once and then written over here. All right, Tom. Well, so we look at the graph is getting a little bit bad. So okay, so here we go. That's not the pointer. This is the pointer. So lots of I/O time, lots of MPI/O time, translating to very little POSIX I/O time. So what's going on here? Well, what we expected to see was, this is like on page 2 of the dharshan job summary output. We expect to see a phase where initial conditions are read, followed by some simulation, where no I/O is happening, followed by a write. All right, well, again, now remember, dharshan is not keeping track of every read operation, just first and last read operations. So there probably is a phase where there's doing a read here of just the initial conditions. And there probably is a phase where it does some writes. But here in the middle, you see read and write happening at the same time. Again, this is the read, modify, write that's happening with a data sieving optimization in the MPI/O level. If you can avoid that, then right, you've got a lot less data movement, a lot better performance. So we talked to Tom about how that's the case, and he said, okay, right, I made a mistake. The headers are spread out through the file strided, and that's why there's holes. And so, well, we can fix that. Why don't we just put all your header information up front of the file or at the end, doesn't matter, as long as it's all together. So when we reorder the file a little bit, and now the I/O time, as you can see here, is actually what we see. More processes mean there's more parallelism available, more I/O links on Intrepid, and the runtime actually goes down, not grows. Sorry, I/O time stays about the same, simulation time, it's a strong scaling simulation, so more processes get done faster. We've brought down the MPIO time to be a lot less. There is collective I/O going on here, so there's some time where there's exchanging of data, but there's not this. We're at a much more manageable level, and as you can see, we're not getting in the way of the simulation. So now his more small computation scales up to 8 racks on Intrepid. The dharshan story can be summarized like this. We have these big systems that have complicated I/O layers, and understanding these tools can take a little bit of extra work. Right? There are lots of tools. You've probably already talked this week about things like HPC Toolkit and various other tuning and optimization, performance analysis tools that work well for CPUs, but for I/O, the story is a little bit different. They don't quite work the same way. So usually trace-based tools are needed, like JumpShot or Tau, but then those require a manual instrumentation step or generate very large log files and can't be left on all the time. So we think a little bit more about how to do our analysis. What's the minimum information we need to make a contribution to improving I/O on these scientists' lives? And so we think carefully about what we need, and we think carefully about how to limit shared resources and how the tools like dharshan can use the collectives that are available to all applications to work effectively. This is on all the time, and we're working on finding ways to automatically, tap the virtual shoulder of people's of application scientists as they run on their I/O systems and catch them before they notice they have I/O problems. The dharshan webpage has a lot of links to papers and a data repository now updated just recently. Some logs from several months or 9 months of Intrepid activity. So if you want to do your own data mining project, there's a good source of information to look at. Quincy is in a collaboration with Berkeley Lab and Lawrence Berkeley Lab and UIUC to auto-tune HDF5 and storage system parameters. They've taken dharshan and they've extended it to not just capture the opens and HDF5 opens and closes, but more detail about what's going on in HDF5 land, and then fed that to an optimizer process that would then figure out the ideal tuning parameters for HDF5, MPIO, and the file system itself. And so that's been, and that resulted in a paper that was accepted to SC. I don't remember the title, but it'll be in the supercomputing technical program this year. Any questions about dharshan before I turn the floor over to Rob for some future technologies? They haven't put it on Titan. You're right. We worked on, the way it goes, we got it working on Intrepid. We went to the Jaguar, and it was not as lightweight as we thought it was going to be on Jaguar. So the Oak Ridge guys are kind of once bitten, twice shy sort of thing. We've had good experiences on Hopper. We can probably try that again now that they can see that it's actually worked well on a Cray machine. That's not so different from what they've got. But the things we thought were lightweight on Intrepid and GPFS end up not being so lightweight on Luster and Cray, so we had to do some adjustments there. And we did, and I think Phil's got it down to pretty low overhead on all platforms now. But if you wanted it on Titan, you'd have to probably build it yourself.
Ask for it.
Yeah, it's a good point. If the Titan people hear from their users that, hey, I heard about dharshan, I want to have it turned on, they probably reconsider it now.
You know about Blue Waters? We've talked with them about it a few times.
He's asking about dharshan's availability on other machines. Titan, not yet. Blue Waters, talking with them too. They know that it's been useful on other platforms.
We've talked with Bill Kramer and some of those folks about it, and it feels like one of those things that we all notionally agree would be a good idea is just not high on the priority list right now. But it ought to be fine on there. And we would, if we can get them sold on it, we'll make sure it's running right. So.
Any more questions? All right. I should have put it on the slide, but if you're on Mira, the logs end up in GPFS, Mira FS0 logs, dharshan Mira year, month, day, and then some long file name that corresponds to your job and username.